Photosynthesis, the light independent phase. So it doesn't need light. It'll still happen while there is light. But this is sometimes referred to as the Calvin cycle. But think of this as the synthesis phase of photosynthesis. We've used the photo phase to generate some ATP and NADPHs. We're then going to be using them to do this synthesis phase where we're actually fixing carbon and storing that energy in the form of a carbohydrate. This is commonly referred to as the Calvin cycle, named after the fantastically named Melvin Calvin. So the net equation for this process involves, here's one way of writing it here. Realize this could be simplified, but essentially we're taking 3 carbon dioxide molecules and we are turning them into a G3P, which I'm sure you remember from our glucose glycolysis breakdown. This is glyceraldehyde 3-phosphate, the product at the end of glycolysis 1, sometimes referred to as PGAL, but this is what we're making. It will then be used, if you make 2 of them, to make glucose. But in order to take those carbon dioxides, we've got to run it through these steps here. We're going to be using ribulose biphosphate, also known as RuBP for short. Notice it's being used, but it's also being regenerated. So essentially, it's not coming in or out of the reaction itself. It's used in the cycle, hence the name. Going in, though, are 9 ATP molecules, which are going to be destroyed and made into ADP, which would then have to be regenerated by the light-dependent reactions. Same with the electron carrier NADPH. We're going to use 6 of them up. And again, they'll have to be regenerated using the light reactions. So you see how the light reactions are used to run the light-independent reactions. I should say the light-dependent reactions are used to run the light-independent reactions. And again, if you want to make a glucose molecule, you're going to have to use 18 of these ATPs, and you're going to have to use 12 of the NADPHs in order to get 1 glucose molecule. So be very thankful of the amount of work these plants are doing to give you sugar. Location-wise, this is happening in the stroma of the chloroplast. So remember, we have our organelle, the chloroplast, which is inside the plant cell itself. And we have these thylakoids inside the chloroplast. That's where the light-dependent part was happening. We were pumping hydrogen ions into the thylakoids lumen using light energy in photosystem 1, photosystem 2. That was creating the hydrogen ion gradient, which was then used to produce ATP. And in the process, during non-cyclical light-dependent reactions, we also produce some NADPHs. These 2 are both going to be used in the Calvin cycle to make not directly glucose, but to make this glyceraldehyde 3-phosphate. Get 2 of them, you can make some glucose. Here's the overall view of the cycle. Again, it is a cycle. We want to know what's going in and what's coming out of the cycle. There are obviously molecules involved in the reactions, both reactants and products. There's going to be enzymes involved in catalyzing these reactions, but we want to sort of understand what's happening with the carbons as we go through this cycle. So carbon dioxide is going to enter the cycle. Do realize that this RuBP, this ribulose bisphosphate, is already in the cycle, so it is going to be where the carbon dioxide is meeting. This first part is called carbon fixation. We're taking it out of the atmosphere. That's often referred to as fixation, and we're taking carbon out, so that's carbon fixation. So plants have been doing this for a while. We've put a bit too much in, but we need to figure out other ways of getting it out. This is the way plants get it out. So they attach these carbon dioxide molecules essentially to RuBP molecules. These are 5 carbon molecules, and so if you throw on a carbon dioxide, or at least the carbon part of it, you're going to end up with a 6 carbon molecule. The enzyme that does this is a hugely important enzyme, the most abundant protein on Earth, but it is a enzyme that catalyzes the fixation of carbon, actually pulls carbon out of the atmosphere, a handy thing to be able to do, and it is called rubisco. So this rubisco takes the carbon dioxide and fixes it to RuBP. This creates, and again, if you've got a 5 carbon molecule, we're going to use 3 of them to fix the 3 carbon dioxides. So you've got a 5 carbon molecule, of which you have 3, so that's 15 carbons. You add 3 more to that, that's 18 carbons. They actually make a 6 carbon molecule. So if you have 18 carbons, you can make 3 of those 6 carbon molecules. They immediately get turned into a 3 carbon molecule. So if you have 3 6 carbon molecules, that would give you, if you turn them into a 3 carbon molecule, 6 of them. So that's the first step there. But this is then going to get reduced using our electron carriers that we generated. So we take our P gap here are three, make sure you get the right ones here, 3 phosphoglycerates, and we are going to be using up some of the ATPs that were generated during the light-dependent phase. We're going to use 6 of them at this point here. The phosphates are going to be taken off. We're going to phosphorylate this 3-phosphoglycerate into 1,3-bisphosphoglycerate. So it has the phosphates on it now. Then are going to be given the electrons on the electron carriers. The electron carriers are going to be losing their electrons, so they're getting oxidized, and so the actual molecules in the Calvin cycle here, this 1,3-bisphosphoglycerate, is going to be gaining electrons, and we know that that's referred to as reduction. So they get reduced into glyceraldehyde 3-phosphate, also known as G3P. That's what we're trying to get out of the Calvin cycle. We can make 6 of those, which sounds great, but only one of them actually comes out of the cycle. The other 5 of them have to stay in the cycle so that we can actually run the cycle again. It's no use just running it once. So when we run it again, we have to regenerate our RuBP, or plants do anyways. And so to do that is going to take some more phosphates. So we're going to have to use 3 more ATPs in order to regenerate our RuBP so it's ready to go to meet some more carbon dioxides and run the cycle again. Take a look at the overall work that has been done here. 3 carbon dioxides are going in. 6 plus these 3 ATPs are being used up, so we're using up 9 ATPs, and 6 NADPHs are also being used up, and that is to generate one single G3P glyceraldehyde 3-phosphate. 2 of those are needed to make a glucose molecule. So you'd use 6 carbon dioxides, which makes sense. Glucose has 6, that's where they're coming from. We're going to be using not 9 but 18 ATPs, and not 6 NADPHs but 12 NADPHs to run the cycle twice. That'll give us 2 of these G3Ps, which will be then able to be converted into glucose. That process itself is involved, but this is the G3P that we get out of running the light independent reactions. They are then able to be eventually converted into glucose, or sort of like a disaccharide sucrose if you use 2 of them, but you're going to have to run the Calvin cycle twice to get 1 molecule of glucose.